Finder. Is it recording? Let's see a stop sign. Question was not enough space left on device. This can happen when the disk is actually full. Yeah. If you try to write in the scratch directory on the head node, that thing's already almost full. So it depends on where you're trying to write, whether you can do it. But all the files that I asked you to save shouldn't be, nothing should be super large, I think. So I would have to actually see it to help debug that, I think. So if you want to come into office hours today, we can try and figure it out. Yep. But using it from Windows, that sort of thing shouldn't matter at all. It's just a client. Yeah. So but can mean that the disk is full. Any questions? Yeah.
How do you use the SFTP protocol?
How to use SFTP? How to use SFTP. So I can demonstrate that real quick. Okay, so I'm let me make this not a little bigger maybe, and that. So SFTP works as follows. SFTP, your username. So Clark F is my personal username at gauss.csc.ucdavis.edu. Then it'll say connected. It'll prompt you for your password for your student account. So you'll enter your password there and press enter, and you'll connect just like you do with SSH. I do ls, and that's a ls on the remote server. So this is me interacting with the head node on Gauss, saying, what do you have there? It says it's got a folder name R, data, dev, PhD research, projects. I can navigate in this file directory just like I did with my local one. So cd projects and ls, and cd sta 141c-homework 4. Changing directories on my remote ls, and here I see everything that has been output, the .out script, the homework4.sh, submit.sh, all these things. To get them, I use get command, get submit.sh or whatever I want. Okay, and that says it's bringing it back 100% done, so it already got it.
Your local machine.
Yeah, so what this did was get, so I was logged into the remote machine, I said get, so get the result and bring it back to my local machine. Now it is on this local machine, and I can verify that with LLS, local ls. I just got submit.sh, and now it exists on my local file directory.
Okay, and the SCP works the same?
Yep, SCP is just the same. It's just you, with SCP it's not interactive, you just do everything all at once. So you SCP your name at the remote host and then specify the file on that host.
The same command.
Yeah, all in one. I mean, I can demo it for you also if I remember the syntax. And to get out by, or exit by being a different way. So let's see if I can remember how to do that. SCP. Okay, so this is the form user at host port path. Okay, let's see if we can do that. SCP Clark F. at gauss.csc.ucdavis.edu. That's my username, the host, and the path is, I had it in project, for my home directory I had it in projects, STA 141.
I think we need to do the initials slash.
You mean an absolute path?
No, if somehow just it's required.
Okay. So I'm just going to try it and see what it does. And then we'll try and add that if I don't. Let's see, 141C C slash homework 4 slash so that was homework 4.sh. There should be one file that I have there. Okay. So that worked. So and now if I do a local ls, I see my homework 4.sh. So I could have given it an absolute path, but it looks like this relative path, it just took it to be relative to my home directory, which is where it puts me when I log in to the head node. Yeah. So then I do it all. You would still have to enter your password and all that. But yeah, two ways of doing the same thing. SCP a little bit easier to automate. The only important thing to remember there is, well, I can ask you this. Do you think you could do these same commands from the server to your machine? Do you think that would work? No? Why not?
You need a local repository, right?
I mean, I have a local repository. I've got lots of local files on
It's
that.
not that sure, but I did try doing it from the cluster. It didn't work.
Yeah, so you could SSH into the cluster and then try to SFTP into your local machine. Problem with this is your local machine is generally not accessible from the wider internet. So the whole internet and the whole world can't go, I want to SSH into Clark's machine. That doesn't work, and for good reason. Unless you set it up, like you have a dedicated IP address or dedicated host name and you pay for these things and you set them up and you know what you're doing. So this is what people do when they set up web servers. And of course all of our servers on campus are set up to accept these incoming connections because that's the only way we can interact with them. But you can happily go from one, like the head node, to a different server to any other server, and you can kind of transfer data SFTP back and forth between these servers. That's all fine and good. That's how I got the data on it in the first place. Okay. Okay, so just demo that. Any other questions? Yeah, Jared.
Oh, can we use problem 2.2 to ask whether or not IDs match? The question 2.2 asks if the IDs are matching.
Question 2.2 asks if the agency IDs are matching.
Yeah, can we use R to test?
Yeah, use whatever you want to. Can we use R? Sure, use whatever you want.
Also, I feel like you can look at it in many ways, but it's pretty hard to get absolute certain guarantee that they don't match.
All I was asking you to do was compare the IDs, like the integer
So when you
IDs
guys
of them.
look at the IDs in one file and then check the description, and then the ID in another file and check the description.
I wasn't even thinking that. I mean, you could to be doubly sure, but I was thinking just the ID numbers.
So are
Have people done this? Like, are the IDs different in the two data sets? That would be really,
Different.
Wait, do you mean each ID in one set maps isn't present in the other set? Or do you mean that they're just taken from the same set of agencies?
I was asking you to find the set difference of which ones appear in the transactions table, but not the other awards table that we looked at before.
Oh.
That's what I was asking.
Because the total number of IDs are not the same.
Yes, actually, they're consistent.
Yeah, one has more, right?
Yeah.
Yeah.
is
So
that from
Is that you?
So they are not the same.
Yeah, well, I would like to know like how many are there in one and not the other, or something like that. Yeah, or if one is a subset of the other one, that would be worth saying, definitely.
Okay.
So find out which are in one but not the other, or how many. Other questions? No? Okay, do a little bit of review. Okay, so here I have all our lectures and stuff, and I put these links in to what we did last time. One of the links was this list of anti-patterns. So you can see, oh, here's the ones with programming. So last time I talked about magic numbers, but I haven't talked about all the possible ways you can kind of make errors or things that look that don't work well when programming. So the wiki page here was anti-patterns, which are things you should not do. And there's a whole bunch for programming and software development. So I've not gone through all of them. I just said the ones that I think are relevant to this assignment. But feel free to go into this and see what else you can find. I mean, another one that's commonly thrown out there is hard code. So hard coding is, encoding some assumption like that you're sure that it's Windows or you're sure that it's Linux or something like that. Repeating yourself is the other one, another one that we talked about. So those are some anti-patterns. But let me show you a tool that you can actually use to check your code, or one of many tools. So here's my R interpreter. I make a function, fbad equals function of x plus y. Why am I calling that fbad? F for function, bad for bad function. What's wrong with this function?
Here's a y.
There's a y?
Here's no y.
There's no y? But it should work fine, right? Let's see if it works. So if I say y equals 10, and I call fbad on 1, so I run this code, and I try and call fbad, fails because y is not there. I forgot to actually run that line there. So that's not good. But then I define y, and I run it, and my function works. It adds the two numbers. So what's wrong with that?
Why is a global variable?
Yeah. Y is a global variable. And we didn't need to do this. So this is essentially a gratuitous use of global variables. We didn't get any benefits out of it. Sometimes you can use global variables to do things that you want to do, but in this case it's kind of a mistake, I would say. You could give it a default, and that's fine. So to fix it, you can go say fgood equals function f of x and y. And that should be good. Now we can call fgood on 1 and y. And we get 11. So we pull the global variable into the actual argument signature. So it comes passed through in the argument signature. So the thing that I wanted to show you is CodeTools check usage of fbad. Code tools. Library, code tools. Did that happen? And that is not complaining about it being a global variable. That's good. Okay. Okay, so what it did immediately before this class was tell me that this was a global variable. So code tools check usage. And I'll have to look into this and see why it didn't work. But normally with this check usage, it prints something to your screen and says, this is a global variable. It looked at your code and saw that you were using this as if it were a global variable. And it says that that's a problem. So you can use these kinds of static code analysis tools to check your code and see where there might be problems. Another tool for this is lintar. This is another package that will help with this. Remind me to do, figure out what is going on. Figure out why check usage didn't print. Okay. Let me just try one more thing. Oh, I think I maybe know. What if I remove y? Yeah, there, that's what it was. I fixed it. Sorry about that. Okay. So we saw some difference in what check usage actually did. So check usage was operating on our live code. So when I call it now, it says there's no visible binding for global variable y. The difference from before is I had an actual global variable named y in my workspace. That function was finding it when it couldn't find y from the arguments to the function that were called. So besides finding global variables, check usage will find other sorts of problems with your code, and you can experiment with it and see what it does. Any questions on this? Or lintar? Yeah, lintar does a lot of stylistic things too, which are more what I would group in the cosmetic type of category or preferences. All right, that's all I wanted to say about that. Let's talk about the project now. So I have given you the project proposal assignment. So this is due next Tuesday. I'm giving it to you early so you can form groups of 2 or 3 based on your interest. But I want you to help me a little bit today if we can brainstorm and think about what questions we might ask with this data set. So I think it's a very rich and interesting data set, and there's a lot of potential things we can do with it. You've been processing it for this homework, but to just summarize what is inside this data set, we have the date. So we have transactions, everything that the US federal government has spent money on for the last 20 years or something, these big purchases. We have the date, the amount. We have description that's a free-form text and also discrete categories. So categories meaning like office supplies, automobiles, and so forth. We have something called the Industry NAICS code, North American Industrial Classification System code. So that means like mining, heavy machinery, that sort of stuff, whatever the industry that's in, kind of related to the categories. We've got a whole hierarchy of funding agency names. There's agencies and then sub-agencies underneath these agencies, which are all spending money in various ways. We know everyone who is receiving this money, all their names and IDs, and we can find out more information on all these people too. Because there's more tables in the database, and I can look that stuff up for you if you want. Another thing was business categories. So small business, U.S.-owned business, woman-owned business, veteran-owned business, all these sorts of things that the government has mandates to spend money in different ways. So, besides this, you're also welcome to bring in third-party data. Any kind of open data on this that you can find somewhere else, you're welcome to join it in and use that to enrich the analysis. So I'm asking us to think about some cool questions. Like, what would we ask? What do we care about with this? So, one, just to get us started, if we know the transaction description, can we predict what the code is? So we have free text that says what kind of purchase it was. Can we figure out what kind of industry it was? I think that would be an interesting one. But I'm curious to hear what your ideas are for how we can use this kind of data. So we've got all this sort of things. Let's try and list some ideas for questions. Ideas for questions. And now it's your turn to kind of think about how can we use this data and say something cool. Who's got some ideas of cool questions? Just throw them out there. Predict future spending? Predict future spending. Yep, absolutely. I'm sure we could do that by many different categories, right? Future spending by each agency, future spending for each customer or recipient.
Or industries.
Industry, yeah. So there's lots of prediction problems inside there. Yeah.
Look at who's getting the most money.
Who gets the most money? Always interesting. Gets the most money. I met a representative from Northrop Grumman last night. You know Northrop Grumman? It's a defense contractor here, and they have an office in Sacramento. So, I was just thinking Northrop Grumman. I saw a whole bunch of Northrop Grumman industries here, or entries inside the data set that said, X millions of dollars spent on Northrop Grumman developing whatever technology they're making. But yeah, I know him because I almost took a job there, but then I decided to finish my PhD instead. So.
The evolution of who gets the most money.
Evolution of who gets the most money? Okay. For example,
When does the data set start? What is the time frame?
Okay.
No, I'm asking you. No,
Oh, you're asking me? Okay, so there's all these kind of exploratory data analysis things, and those could be part of it, right? So you could imagine looking through the dates and determining this. But I think we saw this in the awards that some of them went out like way past the present day and into 100 years in the future or something. And we thought that some of them were probably typos. But these sorts of things we can also we can determine from the data as part of our project and exploratory stuff. But I want to be a little more ambitious.
Yeah.
Evan.
I was thinking just because we've had all these discussions about border security, we could ask sort of like where border funding is going. And
Yeah.
for what purposes.
Border security. Where is it going? How has it been spent in the past?
Yeah, have the priorities changed in the last 20 years or so?
Yeah, have the priorities. yeah, I mean, if someone addressed this, I think that this would be, people would be really excited to see this. You know, if you publish this on the USA spending thing today, it could also be controversial too. So, so they might not publish it.
I don't think they're going to let it publish.
Yeah, but you're welcome to publish it on your own
Yeah.
platform. It's open data. You just send it to a news agency and say, hey, look what I did. Look what I showed. And that'd be cool. Yeah.
So what's the party preference in which category?
Party preferences
Yeah.
and spending. Yep.
And Democrats would like to spend more money on what kind of data, on what kind of like industry, and maybe Republican has a totally different preference. And
Yep.
depending on who's in the White House, they may be different.
Okay. Yeah, absolutely. And I think I listed that in the.
Already?
Yeah. I'm sorry I didn't show you everything that I did, but we were thinking exactly the same
Oh,
thing.
I didn't know that.
So I listed pretty much exactly that. So it's we're on the same page there. Yeah.
Well, first, would there be duplicates of a recipient if they received it on different?
Yes.
occasions?
Uh-huh.
Okay, so like relating number of times a recipient has gotten funding and like relating that to the date.
To the date.
Yeah.
Like trends. So trends around each person, around each recipient receiving money. Yep. Yeah, so it's not quite a full-fledged question. You'd have to flesh it out beyond that, but definitely rich avenue of pursuit. Yeah,
So another thing I was thinking about dealing with too is we've had a lot of discussions about wildfires here in California.
wildfires, yeah.
So there's like CAL FIRE databases of like fire intensity and frequency. If you have like county spending or things like that, we
Uh-huh.
can maybe ask, is there some sort of correlation between the amount of spending on like forest maintenance and like, wildfire intensity or frequency or something like that? Like, have we changed the way we spend money on the wildland management in California?
Okay.
Is that related?
You mean before and after the wildfire happened?
I was thinking more. I mean, there's like hundreds of wildfires in California.
Yeah.
Annually, right? So if we have like a long-term data set, we could ask, are there some relationships between the purpose or the amount of money that's being spent and some of those factors?
Yeah, absolutely. I've heard it expressed as a complaint that with all these emergency services, they don't ever get the money until like the disaster happens, when
Yeah.
they really needed 1/10 of the money to prevent the disaster or something.
Right. I think it'd be cool too to see if like
Yeah.
there's a year after effect, right? There's a bad wildfire, suddenly funding spikes for that same area.
Yeah.
The year after the fire happens.
The piece of the data set national, have you like look at California specifically?
Yeah, it's national, so you can focus down and focus specifically on California or the west or forested areas where wildfires happen. Colorado and Utah, California. Okay. All right. So I also, there's these questions can kind of guide you, and you can come up with your own. You can use the ones that I've written, do more stuff. But the other thing is technology. Technology. When you form groups, you might well form groups around the technologies that you're interested in. So this survey thing, we got this survey back. It seems like most people are interested in learning more about SQL and Python. Those were the most popular ones. You're totally welcome to use any technology you want for this. You can use the cluster, you can use your local machine, Python, SQL, R, whatever. I can make all this available to you in the database, in like a SQLite database. So if you want to use SQL to query it and develop your skills there, you can do it. We don't have time to do homework assignments to focus on all these different languages. Honestly, we only really have time for one more homework assignment and then a code review, I'm thinking. And then we'll work on our final projects after that, just to give you time to actually do something with it. Otherwise, we'll be spending all our time doing this. So if you want to learn one of these, let's actually, maybe now would be a good time to just get a visual so you can see other people around the room that you might want to talk to be partners for your project if they're really interested in this. So who is dying to code something in C, something really fast? Oh, nobody? Okay. Duncan's going to be so disappointed. He was going to come in and give a guest lecture on C. Maybe the last week or something. Let's see. All right, Julia. Who wants to use Julia for this project? Learn about Julia. I see Rishi is our Julia. No one else? Okay, Evan, maybe. All right. How about Python? Who wants to use Python for this assignment? Okay, now a lot of hands. So look around at who's got their hands up and raise them high. So these are the people you'll want to talk to after class. Who wants to use SQL for this assignment? Lots of hands, a large overlap with the previous set. So you could use two technologies. That's fine also. Who wants to use Spark? We do have a Spark cluster running in the stats department. You can use it. We can get you access. Okay?
Oh, question.
Yeah.
So for Silicon Spark, they are basically databases, and Python is programming languages. Right?
Spark is a distributed memory
Database.
type of framework. Yeah, the database is a big part of it. Yeah, but it's more than a database.
So for the language, I was assuming that the programming language is not the database languages.
No, I mean these are just really technologies.
Technologies.
Yeah, in general.
Why
But-
isn't R listed here?
Why isn't R listed here? Because we've already learned a ton of R and used a bunch of R. These are the survey question was what else do you want to learn in this class? So I will lecture probably on SQL and Python and teach you a bit about them. I just don't have time to give you homework assignments on them. So I will let you use your project and do them and help you out as they go. Okay, so I presume most other people are probably using R for this. Anything else that you're dying to use and you want to find someone else in the class who's you're just a lonely bird out there using Lua and you're like, I know there's another Lua user. No? Okay. Oh. Post on Piazza or something and we can maybe figure it out. Okay, so that's it for the project for the moment. So now we can get on to what I was going to talk about a little more today. And that's shared memory multiprocessing. So, fork. Terms. Define some terms. Terms. Term. Definition. Process. I think of a process as being just a single executing program. So what that usually means for us when we're talking about R is an instance of the R interpreter. So one single R interpreter. When we do the parallelism model where we have all these independent processors working together, each of those R's is a process and they work together. So with a fork, we start out with a single process. And I haven't said what a fork is, I know this. So we have some R. This R process will load data, or will load code. It will use packages like a library. So we have some library favorite library, dplyr. Inside here, we also have something like your data. You say your x equals such and such, your y equals such and such, all these variables that are stored, all this program state that you have. So what a fork does is take one process, so here's one process on one single machine, and it takes the state at one time and makes a copy of it. So the operating system does this. So it takes everything that you have and makes a child. In this case, it would be running another instance of an R process. So what it does is it has a copy on write policy toward all the data. So copy on write. So fork, so what it really does is, let's see, say fork. It creates a child process from a parent process. We like the fork because it's really fast. The operating system can do this very fast. Rather than loading all the libraries up from disk or something, it just takes something, all the stuff that you already have in memory, and copies it and makes a new one in a new location. But they actually share the memory. So you won't end up copying your big data objects inside here, X and Y and all these things. They exist inside the parent process. And you make the child. So you can make just one child, or you can make a whole bunch. And that's what happens inside the R parallel processing thing. So you can have another kind of child sharing all this data. So child 1, child 2, with another version of R running. And these children, they can both see X and Y. So the reason that this matters is because it's fast and doesn't make copies unnecessarily. So low memory overhead. Okay, any questions on this? Does this make any sense to people? It'll make more sense maybe once I demonstrate some of the things you can do with it. Yeah, question?
So just to be clear, you drew it as if they're sharing X and Y, but they actually have their own copy of X.
No, they're sharing it, and it's copy on write.
Oh, I see.
Yeah. So in case whenever the child, and they also share at the time. They have a snapshot at the time that the child is created. If the parent goes on to change X and Y later, the child doesn't see that. Yeah.
Is it like when you save the variables in the environment R, and then somehow you send that environment to someone else, or other variables away?
This is something that's actually deeper. It's going on at an operating system level, and this is also something that Windows cannot do. I'll just mention that right now. So I mentioned we were studying the simple model for parallelism. This is a more complex and richer model where they're sharing and therefore getting some good benefits. But you can do it on our cluster. So yeah.
Wouldn't the processes have separate memory, but the threads have shared memory?
Yeah, so an alternate definition of a process is something that has its own memory space and its own execution thing. But we're not talking about threads at all. So if you're computer science, if you study computer science and you know what threads are, then these are not threads.
Yeah, but the process should have like a separate memory.
Yeah, I mean they do have their own memory. We're kind of trying to represent as this, but when we see that on the activity monitor here, I'll show you how they're not taking up. These large objects inside here are not stored in that memory space, or not duplicated. So that's the big point with this. All right. So let's think about this basic model of parallel where you want to do let's say this stuff space. Work and independent workers. So in serial we do this lapply over some large object x, some function. This is kind of what we do here. With the independent workers, do you remember how we did this? It went from lapply into a par lapply and with a cluster, right? So make cluster and par lapply. Par lapply. Those were the ones that we do here. With a fork, this is where the MC_lapply function comes in. So that's what we're talking about in R specifically. But what I'm showing you is not really specific to R. R just has some implementation of it. Other programming languages can do it as well. So what I want to do here is make clear what the advantage is of doing something like this. So they all have some kind of startup cost. What I'm doing is going to make a table of the times of how long each of these takes. So how long does it take to start up something to do an independent lapply? Presuming that we already got an R interpreter running. Actually, maybe we should start with independent workers. Do you know how long it takes to make a cluster? So, not a long time. It's 400 milliseconds or so on this machine. So that's a pretty specific number, but like on the order of 1 second almost. And so what that does is start up new R processes going through the normal system routes. Just like I type R in my terminal, I start a new R. So this takes about 400 milliseconds to start up. The fork, I was saying, it's quite a bit faster. So since you can just take what you've already got loaded into memory and copy that, is what the operating system does, that's a lot faster. It's about 40 milliseconds. And with the serial, how much time is that? Does it take to... What is the overhead to start up before we can run an lapply?
1 nanosecond, 1 microsecond,
1 nanosecond?
or maybe
What did you say?
maybe 1 microsecond.
Microsecond or something? Yeah, so it's whatever the cost is for an lapply, which is essentially 0 compared to these other things. So there's really no cost to doing an lapply. So let's then do evaluation, or no? So after we start it up, then we have to send the data over. So I need a few more terms. So let's let what did I have here? N can be the number of elements. K be the number of workers. So then we have some constants associated with how long each of these things take to run. So it takes time to actually evaluate one of these. So f, essentially f of xi. Time to evaluate. CS is the time to send. CR is the time to receive. So we can make time estimates for all of these. If we're sending for the independent workers, we have to send those parts of X from the main process to all the worker processes. So this takes some time. How many do we have to send from the manager process? If we've got, what would this time be in these terms? For the independent workers?
How many for each one?
Yeah, so the total time it takes to send them from the manager, we have to send each of n elements, so we have to send n of them. And the time to send, time to send one, time to receive one. Yeah. So this is n times CS. How about for the fork? What would this time be? The time to send. If we're operating on this type of model. 0. It doesn't take any time. Big fat 0. And for the serial, also 0. Takes no time. Okay, so here we see what the benefit of the fork kind of is. We're not paying for the time it takes to send the data to the processors in the first place, to the workers. To actually evaluate it, this time is going to be, we have to evaluate n elements and each one takes CE. How about for the fork? Is that right in CE or something different? No.
divided by the k.
Yeah, divided by k. Because this is why we do parallelism, so that we can have many people working on something at the same time. Same for the independent workers. And then receive the result. So this is pretty much just like sending the input and receiving the output. So we have to send n elements. It costs CR. Time to receive. Same for the, how about for this one, for the MCL apply? Do they have to send or not? Yeah, yes, they do. because it's a copy on write. So they go off, they become their own child process. They compute all the results. They compute all that into their, when they're writing stuff, they're writing it into their own memory, and then they have to actually send it back. They're not actually sharing objects. It's not actual shared memory at that point. So this is the same cost in CR. And for the LApply,
0.
0. Yeah, it all happened locally. So then to get the total time, we just sum up each of these columns and we have our total time for each of these different approaches. So with this, we see that MC LApply will pretty much be always faster than making a cluster and doing the par LApply because it has less overhead and you're not required to send the data. However, because of these various sources of overhead, the startup, the sending, the receiving, evaluation is the only thing that you really have to do. These are all overhead. So this is why LApply just by itself can often be faster. Okay. Any questions on this way of thinking about it? Let's see then how this stuff actually looks inside R. Yeah.
So what's the underlying sys call of the independent workers?
The underlying system call?
Yeah.
Oh. So fork is a system call, is that what you mean?
Yeah.
Yeah, so it's not using a fork. It's creating an R. So like when you type in R to create an R interpreter, there's a few options like slave or something, and let me see. R -- help. Okay. Slave. Okay. So you're actually invoking R in this way with the slave option to create a new worker. So that's what happens. So there's no system call.
Multiple R programs.
Yeah, multiple R processes that are not sharing memory, that are independent. That's what we studied before. We're moving on to the more complex thing. Xiaoxi, you look skeptical.
Yeah, I see this quiet and silent, and slave is making R as quiet as possible. I kind of not understand.
Yeah. So why would that be important for a worker?
I just don't understand what is silent and quiet.
You want your workers to just shut up and work. Maybe that's a really bad way of saying it or something. I don't know. I mean, yeah, it doesn't make sense to have them be printing any output because you don't have an interactive prompt with them, is what it amounts to.
Okay, so what does this silent or quiet do? They just run?
Normally with R you get different types of warning messages and errors, and those print out to standard error and standard output. You can look at them and see them. When you set some of these options, then they don't do that.
So what's the difference between this and option warning ignore?
Warning ignore, it just sets them all for you in a convenient way. Yeah, so not that much of a difference. Okay. Let's see it. Okay, so here's an activity monitor. CPU. Right down here, you see something with processes, 422. So there's 422 independent programs running on this computer right now. And of there's 1,500 threads. We look on here, we can see what all these processes are. Sort them by their process ID. You can see all the Google Chrome Helper screenshot, hopefully it's recording our video, all these types of things. Vim, Tmux, R, Bash, all these programs I normally use. So let's start some new ones. Start a new R. Okay, here's a process. Make some big object. R norm 1E8. I run this. It takes some time. It's making some big object. You can check how big it's going to be. Object.size, a big thing. How big is it? I don't know what that says because I can't read like a computer. Print object.size units equals megabytes. There we go. Close to 800 megabytes. Go over here. We see some R, and it has a process ID 10576. Let's see if that's the same process ID of this one. sys.getPID 10576. Okay? So that's our process. We look at the memory usage, and it's consuming 807 megabytes of memory, which is quite a bit larger than what we actually are using, which for our big objects, which is 760, so we're using more for the overall process because it's got a lot more going on and it also requested more memory. Okay. Any questions on these things? Now let's do the forking. Library parallel. I make a cluster, make cluster, 2L, type equals fork. Run this code, and it ran pretty quick. Here, where I had just the one R that was using a bunch of memory, now I have two more, 10604 and 10601. New processes. 604, 601, let's see if that's what they are here. So I can evaluate that same code, sys.getPID on my workers. 10601, 10604 verifies that the new ones that we saw that aren't taking any memory are these same processes. So here's the great thing. we can use the big object from the children processes. Let's verify that. Do the same cluster eval q. Now let's see what it should be locally. So we have this big. Let's look at the first element. Big one, like this. So some random number, 0.305. Cluster eval q. So when I run this, if I ran it with the independent workers parallel model, we would see an error. It says that this object that you have called big is not available on the workers because you never exported it. But because I created a fork cluster, they're sharing this actual memory, and they know the result. So instead of giving me an error that it can't find it, it returns the result because they have read access to it. So, questions? looking at the memory usage, even though they both have access to the same 750 megabyte object, they're not using any more memory because of it. They just have some minimal amount of memory, 6 or 7 megabytes, for a running R interpreter. And every R interpreter will have at least that much memory. Similar for Python. Python is maybe a couple megabytes last time I checked. Okay. Here's the copy on write. So when I actually write into it, so suppose that I want to change what so they have these read, copy on write copies of the big object. When I set one element to be 100, I change this first element to be 100. What will happen at that time is that it will need to make a copy because it writes. Okay? So we can do that, and notice that actually hesitated. It took some time. It didn't just immediately click through. We can run this same code, see what the value is, a big one. So we verify that it actually got set to 100 from what it was before. So that actually changed. Now when we go look at our memory usage, we see our original R process using 800 megabytes, and these R processes are now using 1.5 gigabytes. Okay? So my question for you is, why 1.5 gigabytes? Why would they be using that much memory? The object that they copied was only 750 megabytes. This is like twice as large. Yeah? They made a copy? Yeah. So it made not one copy, but 2 copies. Oh no. That's bad when these objects are so big. We really want to avoid this sort of thing. So it had to make one copy to get it off the master to the worker, and then it made a temporary copy inside the worker when it did the replacement. So when R does a replacement like this, it makes a temporary copy of the object that you have. So, and these temporary copies just happen to be sitting around in these other R interpreters. So this is kind of a gritty technical detail for why they're there. Those temporary copies have no reason to be there anymore. It's just that the garbage collector hasn't ran on the workers to get rid of them. If we force the garbage collector to run, then that should go down. GC. So GC calls the garbage collector. So basically because it made copies. It made 2 copies. Okay, run my garbage collector. Go back and see what's happening. So now it dropped down from 1.5 gigs to just the 700 something gigabytes because it cleaned up and removed that temporary variable that it made. This is why you got to be careful with copying inside R. The other thing why this is relevant is to our cluster computing. When you submit a SBatch job, you can say how much memory you want to use, and you can promise to use a certain amount of memory. So by using something like the activity monitor or whatever tool to monitor your script as it goes to see how much memory you're using, you can say what that is and set that flag. You don't necessarily have to, but you can. And it's kind of good practice too. Okay. All right, so that was actually setting up the cluster, but let's talk about some actual more convenient ways to do it. So if you have some object, pretend it's large, x equals 1 to 5, you can do lapply x seq, maybe, some function, so we get a sequence. And actually, let me stop cluster, use my best practices here. Getting rid of this. So I called stop cluster, and did you see those processes disappear? So they're gone now. The way this is designed to work is to just simply stop it, swap in the MC lapply where you see lapply. So this is very convenient. It's much more convenient than setting up the cluster, sending the data to the cluster, synchronizing the libraries on the cluster, sending the results back, shutting down the cluster. That's everything that has to happen, and that's everything that MC lapply is doing internally. Basically the equivalent of that kind of stuff. But if your whole program is spending all of its time in an lapply function call, then you can make this swap and get a huge speed up often. Yes?
So how many workers does MC apply to know what to do?
So how many workers? Let's check. How many workers does MC lapply use? The way to find these sorts of things out in general is to look at the help page for it. So MC lapply. So the relevant one here is mc.cores, and you would have to read the documentation to know that that's what it is, but you can set the number of cores that you want it to use. So I can set it to anything from 1 to 8 inside here. And actually this is what it does on Windows. It just does it with 1 core and calls lapply. So it's kind of like a slap in the face. I don't know. At least it doesn't fail. Whatever. So I can go mc.lapply mc.cores equals 2l, something like this, to have it use 2. Yeah. Okay. Questions? So there's also pvec, does something similar. I'll just demonstrate that. Pvec x sign, I think. This is syntax. So this is the same as calling sign of x. Pvec. It's just if you have a vectorized function, it's a little bit different than lapply. I can call sign on each of the ones instead of lapply on all the worker nodes. That's what's going on. So it's a little more efficient. So I'm kind of writing it down. It does something similar, but it's more efficient for a vectorized function. So sign is a vectorized function. It already operates element by element. That is, it does the same thing as sapply x sign. These are 3 different ways of doing the same thing. What the pvec does is call just the sign function on each of the workers that it forks, which is faster than calling lapply on each of the workers.
So pvec is even faster than explicitly calling the functions.
Yep. Yeah. So just a little more efficient, but same basic idea. They're still using forking under the hood. Yep. One other thing to know about is running a command asynchronously. So running a command asynchronously. What does asynchronous mean? Anyone know? Huh? Oh, that's a term. Good term. Asynchronous. Thank you. Long term. Asynchronous means in the background. What does in the background mean? So inside my R interpreter, I call the commands, I get the result, right? Rishi said this yesterday, was to use the not yesterday, in previous class, use the ampersand after a bash command. So that lets a bash command run asynchronously. So ls_an, so it actually printed it out and gave me a process ID. Okay, maybe that's not the best example. So if I had some job that I wanted to run, it would take a long time, and I wanted to get my terminal prompt back, then I want that job to happen in the background. I want to say, you go do this thing, now I'm going to continue working on this. It's kind of like you've got one web page loading, and you go to another web page and wait till it gets done loading, something like that. So that's what it means to run in the background. Maybe it'll be more concrete if I do it in R, so I can make a job. Job equals MC parallel, whatever you want it to do. So I can call sign of X, for example. Okay. So inside here, we see a new R actually popped up when I did that MC parallel. So that made a new process that is running this kind of in the background, and it's ready when I'm ready. So it's sitting here taking up a minimal amount of memory. If I look at job, it actually says what its process ID is, 10697, which is the same as the one that was created. So it's sitting there waiting to return the results of sign X. When I want it to come back, I can do MC collect job, I think, result. Okay, and then we see the same that we had the result for sign of X. So
when
in
it's running in the background and to know whether it's done running, you have to look at the activity monitor.
no, you can, this MC collect function can actually check that for you. Yeah, so you could wait in a loop, like sleep 1 second and then check if it's done. So this is a type of parallelism that's totally different than this lapply parallelism. This is, you can have arbitrary things happening all over the place all the time, which is kind of crazier. And then you just bring them back whenever you want them to come back. But you can only spawn one at a time. Or spawn is another technical term. Make a child, fork, that's what I was looking for. Yeah, you can only do one fork at a time with this MC parallel. With the MC lapply, it forks the number of cores that you want it to run all at one time. It makes that many copies of the child process. All right, so I will go right now immediately to stats building on the 4th floor. I'll either be in the lounge or the conference room. If you have questions on Git, the cluster, anything about the homework, please come now.
How did your job interview go?
It went well, I thought.
Yeah.
Yeah, wait and see. It takes some time to find out.
Good luck.
Thank you.
做得到一定的一个。
Question about the participation score.
No,
How does it count? Like, how does it? It's like do ask questions of Jazzy, but not like weekly basis. Before, like ask questions or. Oh no, I didn't. I asked him today after the discussion. He said
Yeah, cause like they got like, cause like the average is like